Hi, students. Welcome back to Chapter 5 of your chemistry class. And what we're going to talk about today is the different models of the atom, in particular, the quantum model today. So, some questions we had is that the Rutherford model left short some aspects, even though the Rutherford model helped us understand that most of the atom was empty space and that the center was a nucleus. Remember, he used that using that gold foil experiment. What it left wanting was why chemicals or why do atoms change color? It didn't predict, it wasn't able to predict the chemical properties or explain the chemical properties of an atom. So, for instance, why does a horseshoe glow when it's heated? Why does steel and iron um, glow when it's heated? So we needed some more models for that. So let's just do a brief timeline of the models. Of Dalton's atom theory of the atom in 1803, that atoms were particular distinct particles with no internal structure. Thomson comes along in 1897 and understands the concept of the electron. And then the Japanese physicist also suggests that the atom will have a nucleus. Rutherford experiment in 1911 confirms that through the gold foil experiment, and that the electrons move about the atom. So that these electrons, rather than being in Thomson's model, which was called the plum pudding model, just a short 10 or 15 years later, the electrons are moving about the atom. Bohr comes about in 1913, building upon Rutherford's model, and that the electrons move about the atom in an orbital pattern. And as an electron moves from one ring or energy level to the next, that is called a quantum. And then what is now what we're going to talk about today is the current understanding introduced by Schrodinger in 1826 by a whole bunch of mathematical equations is that the electron movement is more like a cloud. It's not in an orbital pattern, it's in a cloud where you only can predict the probability of where an electron may be at one particular. So, and then later on in 1932, James Chadwick discovers the existence of the neutrons which are in the nucleus. So, what we're going to be talking about today, the rest of this chapter, before we get into the periodic table, is the cloud model or the quantum model of the atom. Okay, so let's talk briefly about Bohr's model. Bohr's model proposed that the electron is found in only specific circular patterns or orbits. So as these orbits, we call energy levels or orbits, they will be in fixed energies around that. And each quantum of energy is the amount of energy required to move from one level to the next. And here's an illustration of that. It is said like rungs on a ladder, on a very strange ladder. It is difficult for an electron to move from one energy level to the next. It takes more energy, just like it would take you more energy to climb a ladder that is unevenly spaced. The higher the energy level occupied, the less energy it takes. So up here, it doesn't take as much energy from climbing on these rungs, although it may be awkward and unsafe. It's not as much to move your feet or your legs or your hands between these higher rungs as it is the lower rungs. So it is with electrons as they move from one energy ring to the next. The higher in energy level, the less energy it takes to move. All right, so here's when we talk about the quantum mechanical model. And what does it say about it? It says that the energies are predictions, okay, that determines the allowed energies electrons can have and how likely it is to be in a particular location around the nucleus. What the Bohr model says is that it's in a fixed position and you would know where it is. The quantum model says it's not actually like that. The quantum mechanical model says we can predict in what space, three-dimensional space, an electron may be around the nucleus. And this was brought about by Erwin Schrodinger. He used theoretical calculations, and the result is a whole series of mathematical equations to describe what is now called the quantum model. And it comes from the solutions called the Schrodinger equation. That's a little bit beyond the scope of this class, This is more of advanced chemistry and physical chemistry, but we're just going to touch it here. So think about the propeller of a blade. Okay, the propeller blade has the same probability to be anywhere in this blurry region. You just know that the propeller blade is within this circle, within the diameter of the circle it's making. You don't know actually where any one of the blades are at any one point. You just can predict that it's going to be in this space at one point. So it's very similar to the quantum mechanical model, is that within this electron cloud, imagine a cloud or a three-dimensional spherical cloud around the nucleus, is that the electron is going to be somewhere in this space. Never known exactly where, but the probability is it's going to be in this space, in this cloud right here. So these are what are called orbitals. And so how do suborbitals and principles of energy differ? So we're going to talk about the atomic orbital. The atomic orbital is often thought of as a region of space where the high probability of finding electrons. So this cloud is called an an atomic orbital. Okay, each orbital has a sub-energy level that corresponds to an orbital of a different shape, which describes where the electron could be. So rather than be in a sphere, there are several types of orbitals or subatomic orbitals. The s orbital is this cloud we were looking at earlier, the s orbital. The p orbitals are in three different directions that can be along the x-axis, the y-axis, and the z-axis. So that's why they're denoted px, py, and pz. And there are these teardropped shapes here. So the p orbital, all of this is one orbital, the electron could be within any space along the x-axis, the y-axis, or the z-axis within that orbital. Similar, the D has not only see how the p orbital has one direction at a time. The d orbital is just a little bit more complex. It can be in two directions at once: the x and the y direction, so it's dxy; the z and the x direction, so it'd be dxz, excuse me, and then the dyz and the dx squared minus y squared, and then the dz squared. So this is a little bit more beyond the scope of this class, but what I want you to see is that generally what we're going to learn is that there are three basic shapes: the spherical shape, this teardrop shape, and this sort of maybe fatter teardrop shape when we think about where the electron will be in what energy level. So rather than thinking of them as rings, as the Bohr model says, these are going to be these shapes. So think of the rings as these shapes here, as maybe a simplistic way here. So one thing to understand about the principal energy level is that each energy level, each orbital can hold two electrons. It can hold two electrons. So think of an energy level as you'll see in the next chapter when we talk about the periodic table, is that each one of these energy levels corresponds to a row on the periodic table. So the first row on the periodic table, the maximum number of electrons that is held in that energy level is 2. The second energy level is 8, the third is 18, and the fourth is 32. Just kind of hold on to that in your head in a moment, but these correspond to rows on the periodic table that'll help you really decipher what are called electron configurations later. So this is what the main thing I want you to see for today is that the atom is more not a rings as described in Bohr's model here, but rather clouds. And these clouds can have the s orbital is a spherical shape, the p orbitals are more like a teardrop shape, and the d orbital is a little bit fatter teardrop shape. And that each energy level, 1, 2, 3, and 4, is what we're going to deal with in this class. This is what they will hold. So this will come more clear as we continue on in our class. Thanks so much for your attention. I'll see you soon. Bye-bye.